So thank you so much. Also, thank you so much for putting the Seafloor Explorer season series together. Really cool. Great talk, Jessica. Yeah, that was impressive. Yeah. I would like to report on our work on oceanic transform faults. This has been done mainly with Ingo Grevemeyer, who has an ESC advanced grant on oceanic transform faults and who is leading most of these efforts. And I will show you some of our observational work and some of the modeling work, which has mainly been done by Ming Cheng, who is also online. Yes. There are, of course, many more people involved. Some of them are online today. I did not mention everyone, but let's get going. There. This is oceanic transform faults play an integral role in plate tectonics. We all know that. They offset the ridge axis. They offset them along small circuits of plate motion. What's actually a fun exercise if you look perpendicular to the strike of the transform, or if you look at the focal mechanisms in teleseismic events, which are mainly strike-slip, you map up the Euler pole and you see the integral form that they play in plate tectonics. And in the absence of changes in plate motion, motion along the transform or slip along the transform should basically be strike-slip with no lithosphere created or destroyed. So they are the typical conservative plate boundary. And then this all started when Ingo compiled bathymetric data for all transform faults around the world at different slip rates, different environments. And what you find is that the actual deformation zone, the transform valley itself, is always deeper than the adjacent fracture zones. And this means that subsidence is not following a standard thermal cooling trend. So a lithosphere that starts at the ridge should just subside with its age. But what happens is when it passes the opposing ridge transform intersection, there seems to be a rejuvenation event or magmatic addition event. Something is happening and we get an anomaly in the subsidence rate, and the fracture zones are always shallower than the active transform faults. And that is a feature that occurs over all spreading rates. It scales a little bit with age offset, as so many things that transforms, but that is basically the background. And based on these observations, Ingo Grevemeyer got the ESC Transformers Advanced Grant funded, which looks into the seismicity and overall geodynamic functioning of oceanic transform faults. And by now we had multiple cruises going to Oceanographer and other places. They were started in 2001 with the 2 Meteor cruises to do OBS work, so seismicity that I will show you, sampling, rock sampling, mapping. We also had a geodesy network deployed. We don't have the results yet, so I can't report on that. We did classic geophysics, magnetics, and heat flow measurements, and also looking for hydrothermal activity that I will come back later to. And the goal is to understand the structures. Already looking at Oceanographer, the structures are puzzling. You have the deep transform valley, you have the shallower fracture zones, you have a little bit of oblique structures. You see this kind of mass wasting here, the oblique faulting, the nature of the nodal basins. A lot of questions to be addressed on how these systems work. Me being a geodynamic modeler, or I used to be full-time geodynamic modeler, now I do more hydrothermal systems and more mapping. But we try to do simple models of oceanic transform faults. And simple models means you need 3D, so it's not super simple, but otherwise they are simple. What we started out was with models that have a kinematic top surface boundary condition, so not a free surface. You drive it by plate motion and see how mantle flow and deformation localizes below. And you find that basically you always go into this oblique mode. Whatever you do in terms of viscoelastoplastic rheologies, as long as you put in like some sort of plasticity, what you always reach is that you have an orthogonal plate boundary on top, and below that, everything transitions into a more oblique shear zone. And that would mean if this obliqueness is existing, and in the models, it's driven by the age offset, which causes an asymmetry in strength. Yes. If that holds up, we would have a mechanism that causes extension in transform faults, and that would mean that oceanic transform faulting includes an extensional component, and that potentially makes the deep floor transform valleys. Yes. When I did those models there, I kept it simple, so I didn't have a free surface and I had some other simplifications. We also didn't have the magmatic component, so no addition of material, no crustal formation in those models. Ming Cheng joined us last year, and he's using LaMem, the code developed by Boris Kaus at Mainz University, and on top of this, it's a mark and Sal code that has all the complex rheologies and a free surface implemented via a sticky air layer. And in those models, you can include the classic formulation of the magmatic component, meaning something like an M factor, like a source term in the mass conservation equation that adds material depending on a magma flux. And Ming is using the magma flux formulation from Jean-Arthur Olive, yeah, which basically relates the amount of melt produced, either computed or parameterized, and then it's added in the brittle region. And that results in a prediction on the M factor, so how much of the extension is compensated by magmatism. So in these models, the question is if the observations we had on the obliqueness driving the extension and causing the valley would hold up there. Luckily it does. I'm kind of relieved to see it in a different code and in a different set of assumptions and more complete rheologies. What you find is models like that. This one is, you see the orthogonal plate boundary, you see a map view or the bathymetry. HC is related to the magma flux, so we produce magma at a rate that compensates for 5 kilometers of crust, which is, at this case, a pretty high M factor, close to 1. And here the M factor is more close to 0.5. That results from the reduced magma flux coming from a robust ridge segment into a more magma-starved segment end. The structures that you do is more or less symmetrical abyssal hill faulting in a robust system and then a deep transform valley. If you have a more reduced magma flux going into the ridge transform intersection, we produce nodal basins, we get core complexes due to detachment faulting. And when you plot up sorry, I have to move you guys out of the way, there. If you plot up the separation axis, so basically where the horizontal velocity Vx becomes 0, you get solutions like that. The more robust the magmatic system, the less oblique the resulting plate boundary, where you get the separation of the two plates. The less magma, the more oblique it becomes, and it goes, basically recovers a more simple solution we had before. If you plot it up in a more complex way, this is a new figure that Ming created. One has to need a little bit of time to get used to that. So you have the magmatic accretion axis here. This is basically the one ridge. This is the other ridge. Then this would be the orthogonal connection. There are two planes plotted. One is the brittle ductile transition, which here is approximated by the 600-degree isotherm. That is this one going into the ridge axis and then to the other side. And then there's a second plane plotted, and that is the plane of Vx equals 0. So the kinematic or the mechanical separation axis that goes into this oblique structure. It mimics a little bit the seafloor. So you also see the ocean basins, the nodal basins here. And you get structures like this where you get the oblique separation that thins out the crust. And we can basically explain the structures we see. So if we look at a transect that looks like that, from A prime to A, in a more magma-starved environment, we would get core complex formation, nodal basin formation, and then the mechanical separation offset to that. In a more magmatic robust system, we would have thick crust, normal crustal thicknesses, and a more connected way of magmatic accretion and kinematic separation. The predictions from these models is that the more oblique, the thinner the crust. That is something one can test with gravity. So we also did classic gravity studies on transformer fracture zone settings, pretty much like the well-known paper on transforms to ridge comparison. What we have done here is to look at the gravity anomalies in transform faults and in fracture zones and see if we get a systematic difference in crustal thickness. The workflow is that we start from multi-beam data and satellite gravity. Then we compute the normal mental Bouguer anomaly, do a thermal model on top using our 3D models. From the thermal model, we compute the thermal correction, and then we get the residual mental Bouguer anomaly. So it's a pretty classic workflow just coupled into our thermal models. And what we find is that we get typical solutions like that we find regions of relatively thinner crust in the transformic domain. and relatively thicker crust in the fracture zone. So consistent with what we saw in the initial bathymetry and consistent what the models tell us. This. If you plot that systematically, one can do plots like that, where you do the average residual mental Bouguer anomaly, so the one corrected for crustal thickness and temperature, and do the difference between transform fault and fracture zone. These are always positive. That would speak to the thin crust I just talked about. But one has to be a bit careful about the baseline because there's this well-known discrepancy between inside corners and outside corner crust that has been known for a long time. If you account for that, you see that there's a systematic difference between inside corner and outside corner crust. So the inside corners have these typical tectonic massifs, the outside corners not. But if you correct for this baseline, you still find this. I don't have time to explain the baseline, but this basically means that it accounts for the fact that in the fracture zones, you have a superposition of inside corner crust and outside corner crust, while the transform fault has a superposition of two inside corner crusts. So you take that baseline out and still all values are positive. And what that means is that the transform fault has thinner crust than you would suspect. That means the transform faults have thinner crust than the fracture zone crust systematically in all the transform system we have studied. And that ties into the separate observations. For example, Milena, I think, is also online. And she looked at the seismic structures, and also there in the paper from 2020, you see that fracture zones and transform faults seem to have different crustal thicknesses, with transform faults having the thinner crust. And that looks like a more robust signal. What one can take this a little bit further is to look at the seismicity structure of them and try to tie in the model predictions with the seismic observations. And what we have done here is to take Mink's models of the full system with the free surface and the magmatic component, and for different realizations with different magma fluxes, looking at the seismicity pattern at different depth. So this is basically taking the stress field of the models, post-processing them into the beach balls, and then with the beach balls we can compare to the seismic moment tensors. What you find is interesting, that we often predict normal faulting in the inside corners and strike slip behavior only in the central part of the transforms. That is what most of these models look like, that you basically transition due to this obliqueness, you transition from extensional tectonics in the inside corners to strike slip in the central transform domain. And that is something we can test against observations. So Ingo and team deployed OBSs in 2021 for 2 deployments. One was cut short. This is a study of microseismicity. The colors correspond to OBSs and OBHs. Some recorded for the full period, some only for 2 weeks because then the cruise was cut short. What you see is a different results here. Where we had a reduction in the network for the stations that were left on the seafloor. You get a pretty consistent picture already from this data set. We get the big strike slip seismicity in the center of the transform. There's also clear segmentation. We see this pressure ridge in here. To the east of it, there's much more seismicity turning into the inside corner, while the western segment on the west side of the pressure ridge is characterized by deeper seafloor and less seismicity. That is clear in the seismic moment release, that the eastern segment has much more seismic moment release than the western segment, so clear segmentation. And if you plot up that versus depth, we also see a segmentation in it, that the deeper seismicity is on the western part, but much less so. And then there's much more seismicity in the eastern part. What's interesting on the top figure, this is from the paper by Ingo from this year, they plotted the teleseismic strike slip events. All the bigger than magnitude 6 events all occur in the west, and there seems to be higher moment release in the teleseismic events in the western part and not so much in the eastern part. This could be interpreted that the eastern part is more creeping and the western part is more locked, creating like the big strike slip events. That is one interpretation. We are not further in that. What could be the reason for that? We just heard that serpentine is maybe not the case. This. What we also see is the seismicity on the inside corners. That goes into this faulting structure. What's interesting is that if you map old microseismicity studies from different transform systems onto modern multibeam data, you see very similar patterns. So this is again Oceanographer, then in B we have VIMA, Atlantis and Kane. And it's actually quite nice to do old seismic data on top of new multibeam. And we see a pretty consistent pattern that we get basically these normal faulting events in the inside corner, and the seismicity transitions into the inside corner is not localized along the transform strike in the inside corner regions. This. Final statement on that. I told you I like fluids now. So when I see all these results I just showed you, normal faulting, magma, heat, everything in the inside corner, we were immediately thinking of hydrothermal activity. Ingo and me have no track record of looking for these systems, but we took the NOAA MAPA systems with us, which look for water column anomalies on the last cruise we had last year. We deployed these guys. I'm turning slowly into more a seagoing person. This. And the cool thing is we actually found something. So this is a picture I took off my computer when we were doing the Toyos down the inside corner of Oceanographer. You see the first processing with the first anomaly in the turbidity. This is a bit more nicer processing, basically going down these big faults in the inside corner, in the western eastern inside corner. This is one of the big faults there. And right there we found this big water column anomaly. The captain told us to leave. We were not able to take water samples, so we don't know if that would hold up in the water chemistry. We need to go back yet another time. This is where it stands. I think what we find now is in models and in observations that transform faulting can contain this extensional component, that the valleys have a thinner crust than the fracture zones. Seismicity transitions from normal faulting to strike slip in the main domain. What I showed you from Mink's model is that the way the models are set up now, maybe it has to be done better where the melt is actually in place, but we see this disconnect between the magmatic and tectonics separation axis, basically, and that is what is most likely creating the nodal basins and what is creating these tectonized inside corners. And then it seems like that the eastern corner of Oceanographer is hydrothermally active, and I think we should look better to see if those are regions of enhanced hydrothermal activity. Thank you very much.